But what happens when blood sugar dips, say, between meals or overnight?
Right, that dip is the next signal. This time the pancreas releases a different hormone, glucagon.
Glucagon, the opposite of insulin, basically.
In many ways, yes. If insulin says store, glucagon says release.
It's not just glucagon, though, is it? I feel like there are others involved when things get low.
You're absolutely right. Your brain picks up on that falling glucose, too. It signals the adrenal glands.
Adrenal glands. That means adrenaline.
Yep. Epinephrine, that's adrenaline, and the norepinephrine, plus cortisol. They're like the backup crew.
The cavalry coming in.
Yeah. To make sure you don't run out of fuel.
So what do glucagon and this backup crew actually do?
Okay, so in the liver, glucagon and epinephrine team up. They tell it to break down that stored glycogen back into glucose.
Releasing the savings.
Exactly. And they also start making new glucose from other stuff. That's gluconeogenesis.
Fancy word for making new sugar.
Pretty much. And the liver pushes this glucose, plus some ketone bodies, another fuel source, out into the blood.
Ketone bodies. Okay. And what about muscles in the liver itself? Are they still using glucose?
Good question. They actually start to switch fuels. They begin burning fatty acids. So let's start with, like, the basics. When we're fasting, what happens in the liver? Like, it doesn't have its usual glucose coming in, right?
Right. So the liver has to adapt.
Yeah.
It basically turns to stored fat.
Okay.
And starts breaking it down for energy.
Got it.
And that process is called beta oxidation.
Yeah, it's like dismantling these stored fuel reserves. Okay, so it's breaking down fat. And when it breaks down fat, what happens?
Well, you get this byproduct called acetyl-CoA.
Acetyl-CoA, right.
And it starts to accumulate in the liver.
Okay, so the liver's breaking down fat. We're getting acetyl-CoA. Now what?
So that's like the critical trigger.
Okay.
When the liver has enough energy for itself from the fat breakdown, all this extra acetyl-CoA starts building up.
Gotcha.
And instead of just wasting it, the liver turns it into something useful.
Okay.
Ketone bodies.
Oh, okay.
Acetoacetate and beta-hydroxybutyrate.
So it's like this excess acetyl-CoA gets converted into ketone bodies in the liver.
Exactly.
So the liver's like the factory.
The liver is the factory.
Got it.
It's the main production site for these ketones.
Okay, but they can't just stay there, right?
No, they can't.
They have to get out to the body somehow.
Exactly. And that's where it gets really interesting.
Okay.
See, acetyl-CoA itself, it's not easily transported out of the liver. But ketone bodies, they're different.
Okay.
They can dissolve in the bloodstream and travel to other tissues.
So they're like little energy couriers.
Exactly.
Going through your blood.
Yeah, so they're like a readily available energy source for other tissues.
So which tissues can actually use these ketone bodies?
Well, a bunch of important ones. The heart can use them.
Okay.
The brain can use them.
Oh, wow.
And even skeletal muscle can use them for energy.
Okay, so like pretty much everything.
Yeah, it's a really important alternative fuel source when glucose is scarce.
Especially when you're fasting, right?
Exactly.
So here's something that I thought was really interesting. They mentioned this in the Metabolism Made Easy video.
Yeah.
Even though the liver makes all these ketone bodies, it can't use them itself.
Right. Isn't that wild?
It's so weird.
It seems counterintuitive, but it's actually really clever.
Why is that?
Because the liver's main job in this whole process is to just produce the ketone bodies and then export them to the rest of the body.
Got it.